In this video, you will learn how to graph the other trigonometric functions. And the other functions we'll be talking about are tangent, cotangent, secant, and cosecant. So jumping right in, we're going to talk about the graph of a tangent function. So what we're going to do is we're going to plug in different values for x and then figure out what would the tangent of x be. So if you plug in here as 0 for x, tangent of 0 would be 0. And we can graph that point here at 0, 0. And notice on this graph that we have down here, we have different locations. We have pi over 12, pi over 6, pi over 4, pi over 3, and etc. And here, if we do tangent of pi over 12, this is not one we do as often, but you can plug that in to your calculator and you get 0.27. And then if we did pi over 6, tangent of pi over 6 would be square root of 3 over 3, which we plotted right around here. And then pi over 4 for x would give you 1 for y. That can be plotted right here. Pi over 3 for x would give you square root of 3 for y. And then if we do 5 pi over 12 for x, we would get 3.7 for y. And then if we did pi over 2, that would be undefined. So at pi over 2, we have what is called an asymptote. So it's going to be represented by a dotted line, and it's basically a location that the y value could never be defined at. It's never going to actually reach that value. So we see the curve is approaching upwards and it's getting closer and closer to the asymptote, but it's never actually going to reach it. Now on the other end, if we did some negative angle measures, so if we did negative pi over 12, negative pi over 6, negative pi over 4, etc., that would give you all these negative y values, and that would create a curve like this heading down towards the other asymptote, which would be at negative pi over 2. All right, so it's going to be something like this, where the curve, if we connect the dots, is going to look like this, where it approaches your asymptote here on the right, and it's going to approach the negative pi over 2 on the left. And this is the general shape of a tangent function. All right, so it's going to be increasing from left to right. And then cotangent, we'll talk about that more in a little bit, but it's basically the inverse of all of these. So instead of increasing like that, it's going to be decreasing something like this. And that's going to be the shape of a cotangent function. Now let's talk about some properties of the tangent graph. Now the domain would be all real numbers except for it cannot be odd multiples of pi over 2, because that is where your asymptotes are located. And we can verify that as well if we think of tangent as sine over cosine. All right, cosine, if you have a fraction like this, the cosine of x cannot equal 0. And where is that happening? Well, the cosine of x is equal to 0 when x is pi over 2, so at 90 degrees, or at 3 pi over 2, which would be a negative 90 degrees, or 270 degrees, and it's going to keep repeating like that. So every odd multiple of pi over 2, it would be undefined. The range, the y values, would be all real numbers, because remember it was going down and then up like this. It's going to go up forever and down forever, meaning y can be anything. The period is actually different than cosine and sine. The period for tangent is pi. If we look back here at the graph that we had, notice that everything falls here in between pi over 2 and negative pi over 2. So if you add that length together, so from 0 to pi over 2 is pi over 2, and from 0 to negative pi over 2 is another length of pi over 2. That gives you 2 pi over 2, or pi. So the period, as we see here, is going to be pi. Everything falls within that range of numbers. And then we have symmetry as well. And the symmetry is about the origin. So if you imagine graphing this, something like this here. Okay, it's going to be symmetric about the origin. And then we have x-intercepts as well, and the x-intercepts will be at multiples of pi. We saw with the graph that we had that that it crossed over right here at 0, 0, right? And we had the asymptotes here and over here. But if we keep going on the other side, we're going to have another of the same thing. It's going to go up like that, and then kind of down like this. This right here would be at negative pi. And then same thing on the other side. We don't have room for it, but it'd be at positive pi, and then another one at 2 pi, 3 pi, and etc. And then we also have vertical asymptotes, as we mentioned, at odd multiples of pi over 2. All right, because that is where the domain is, right? The domain, the x values, can be anything except for odd multiples of pi over 2, because they're asymptotes at those locations. And then also, for graphing purposes, we want the asymptotes, we want the x-intercept. We'd also like to know at least maybe one other point up and then down, like above 0 for x and then negative for x as well. And that can be located by this method right here, where basically we take pi over 4. All right, so halfway between 0 and the asymptote, if we take positive pi over 4, I guess plus k times pi, so it can be, pi over 4, or it could be 5 pi over 4 or 9 pi over 4. But here, just for one cycle, look at positive pi over 4. The y value is going to be up here at 1. All right, so whatever the amplitude is, we'll talk more about that in a minute, that's where your y value is going to be. And then if you go over here to negative pi over 4, so halfway between 0 and the negative asymptote, your y value is going to be down here at negative 1. And that would give you 3 points for the graph, and that would help you create the curve. So talking a little bit more about the graph of a tangent function, we mentioned the amplitude. The amplitude, just like with cosine and sine, is determined by this number out here. So the amplitude is going to be the absolute value of that number. So here we see 3 different functions. Here in red we have our regular tangent function, and then in black we have the y equals 2 times tangent of x function. And then in blue we have y equals 1/2 times tangent of x function. What I want to point out here specifically is comparing the graphs. Notice that ignoring the far left and the far right, just this middle graph right here, notice they all go through the point 0, 0. That is worth noting. So the other question is how steeply is it rising? So in red we have tangent of x. Notice the asymptotes is at pi over 2 right here, and then at negative pi over 2. So we mentioned on the previous slide that if we find the halfway point between the 0 and then the asymptote, so here at pi over 4, we can find another point by looking at the amplitude, the number in the front. So for the red one, y equals tangent of x, amplitude is 1, so it's going to intersect here at positive 1. And then over at negative pi over 4, halfway between 0 and negative pi over 2, it's going to go down to negative 1. And that's where we get this point on the red graph. And then looking at the black one, y equals 2 times tangent of x, if we go over here to pi over 4, our y value at that location would be up at positive 2 right here. And that's how we get this second point. And then if we go to negative pi over 4, we can go down to negative 2, and that gives you this other point on that graph. And then with the blue one, y equals 1/2 times tangent of x, same exact logic, where if we go to pi over 4, we go up 1/2, and that gives you the point right here on the graph. If we go to negative pi over 4, we go down 1/2, and that gives you this other point on the blue graph. So that's what we need. We need to figure out the asymptotes. We need to figure out the x-intercept, which for tangent would always be through the point 0, 0. And then find 2 other points in order to figure out how steep the graph is going to be. So we talked about what happens if you have a number in the front, so something like a times tangent of x. Now what happens if you have a number with the x term as well? Now just like with sine and cosine, this number here will affect the period. That's going to affect the asymptotes. Now the period is going to be a little different with tangent, because with tangent, okay, the period is going to be pi divided by our b value. All right, and if you think through that, tangent repeats itself. That the period for a tangent function is typically pi. We've discussed that in a previous lesson, the logic behind that. But here, this b value would be divided by pi to find the period. And that's why it's pi, though, is because the regular period of a tangent function would be pi. So, for example, if we had tangent of 2 times x, we would do pi divided by 2. If we had tangent of 1/2 times x, we would do pi divided by 1/2, which would give you 2 pi. So that would give you the period. Okay, and we mentioned with graphing, it starts at 0, 0, and we would have over here the asymptotes on one side and then asymptote on the other side. So if you're trying to figure out those asymptotes and the cycle of this, okay, the period is all the way across, right? But to figure out how far to go, right and left, that's going to be half of the period. So it's going to go all the way over here to p over 2, and then over here to negative p over 2. So one complete cycle is going to be where x is between negative pi over 2 and positive, negative p over 2, and then between positive p over 2. And again, 0, the point 0 is a 0 of the function. It's going to look something like this. All right, and we also know, as we mentioned, we can find the other point up here and then down here by figuring out the amplitude and then finding those locations which are halfway between the 0 and the asymptote. And then also we would have asymptotes at every p over 2 location. I guess every odd multiple of p over 2. So we have 1p over 2. 3p over 2 would be a next one. Over here would be negative 3p over 2 would be another asymptote. So every odd multiple of p over 2 is going to be another asymptote. So let's try one out right here. We have y equals 1/2 times tangent of 2 times x. So first off, right here, that would be your amplitude, 1/2. And then we can also find the period. So the period we find by doing pi divided by this number. So pi over the absolute value of 2, which would be pi over 2. All right, so we have already pretty much everything we need. So when you graph this, we know that the period is pi over 2. So we need to take half of that. So pi over 4, we take half of pi over 2. That's how far to the right we're going to get our asymptote. And that's how far to the left we're going to get our other asymptote. So we have here, this would be at pi over 4, and this is at negative pi over 4, because the total length between these asymptotes would be pi over 2 to get one period. All right, so we have that information. We also know that with tangent, it's going to go through this point here at 0, 0. And then we just need to figure out how steep is it going to be. Because with tangent, we know it's going to be something like this, right? So if we go halfway between the 0 and this asymptote, we would find our y value by going up 1/2. So if this is 1, we would go up to 1/2, which is right here. That is 1/2. And then down here, if we go to the left, halfway between 0 and the negative asymptote, we would go down negative 1/2. So if this is negative 1, this would be negative 1/2. That would take you right here. So what we do is we create a curve through these points, and it's going to approach the asymptote up there, and then down here it's going to approach this asymptote. And that would be the graph of this function. And then if there was a negative in the front, so say it was a negative 1/2 times tangent of 2 times x, basically what's going to happen is this is going to be switched around, where the shape is going to be decreasing, so something like this. So it's still going to go through the point 0, 0, but instead it's going to have a point here, and then it's going to have a point down here, and it's going to approach the negative x-intercept like this, and then it's going to go down like this and approach the positive x-intercept right here, or asymptote, sorry, not intercept. It's going to approach the asymptote right here. So the negative just flips it around like that. And then keep in mind, by the way, that there would be more of these. So after pi over 4, if you went over here, so went over another length of pi over 2, which would take you to 3 pi over 4. We would also have another asymptote here, and we would have right here a 0. It would go up right here, down right here. You'd have another graph like that. So this would continue on forever, okay, where there's asymptotes every pi over 2 away from pi over 4 and negative pi over 4. So there'd be some on the left side as well. Now let's talk about the cotangent function. So some properties of the cotangent graph is, first off, the domain would be all real numbers except for, in this case, multiples of pi, which makes sense because if you think of cotangent as cosine over sine, sine cannot be 0, right? Because otherwise this would be undefined. So where is sine equal to 0? Well, sine is equal to 0 at 0 when x is 0, or at 180 degrees, or at pi, so sine of pi, and then back at 2 pi, and then 3 pi, 4 pi, basically anywhere here at 0 or over here at pi is going to be undefined. And then the range, just like with tangent, would also be all real numbers. And the period as well would be pi, just like it was with tangent. And this one has symmetry. And the symmetry would be about the y-axis. So not the origin, but the y-axis. And then we're going to have x-intercepts at odd multiples of pi over 2. And we're going to have vertical asymptotes at multiples of pi, which is where the domain would be undefined, right? At multiples of pi, that's where your asymptotes are going to be. So when you're graphing this, it's going to be very much like the tangent function. The main difference is it's going to be graphed like a negative tangent function, in the sense it's going to be going down like this, approaching different asymptotes, and the asymptotes are shifted differently than it is for tangent. But other than that, it's pretty much the same logic, same steps for graphing as with tangent. And we see here an example of the graph where, again, the asymptote would be here at 0, and then it would be here at pi. You'd see it again down here at negative pi, and this would continue on. It'd go, on for infinity, so negative 2 pi, negative 3 pi, etc. And this is what your cotangent would look like. So when you're graphing a cotangent function, such as this one, where we have y equals a times cotangent of b times x, the amplitude would still be a, and the period would still be found by doing pi divided by this b value. So as we mentioned, one cycle is going to start at 0, so the asymptote would be at 0, so it's kind of shifted over, and then it goes to pi. So one cycle would be from 0 all the way to pi, as opposed to the tangent function, where it was the 0 was the center. So tangent was like this, where you have your asymptotes at negative and positive pi over 2. So that's the difference. This was tangent over here, and this is cotangent. Tangent would go up like this, and then cotangent is going to go down like this. And with cotangent, if we do 1/2 of the period, so right here in this case it would be pi over 2, that gives you this point right here. And then if we found 1/4 and 3/4 of the way between 0 and pi, we can use that to find a second and third point, where here at this location of pi over 4, we would go up to the amplitude, whatever that is, whatever the a value is, and that would give you this point. Then over here at 3 pi over 4, we go down that same distance of negative a to find that third point. Then you connect those dots with this curve. So let's try an example here where we are graphing y equals 3 times cotangent of x over 2. So first off, the amplitude would be 3. We have that right here. And then the period would be found by doing pi divide by the b value. And remember, the x over 2 is the same thing as 1/2 times x. So 1/2 is your b value. So what we're doing is pi divide by 1/2, which is the same thing as multiplying by 2 over 1, which is 2 pi. So the period is equal to 2 pi. So from here, we have everything that we need to graph. So let's do that here. Let's make this 0. And then 2 pi is going to be, let's put it right over here. And at 0, there's going to be a vertical asymptote like this, and then one at 2 pi as well. All right, and then with cotangent, we know that the graph is going to go down something like this. And we know that the 0 is going to be halfway between 0 and 2 pi. So it's going to go through this point. And then if we look here and here at these two locations, we can find your y value. So if we look here, the amplitude is 3. So we go up 1, 2, 3, down 3, 1, 2, 3, negative 3. Okay, at this point right here, so this is pi, this is half of that, pi over 2, this would be 3 pi over 2. At pi over 2, if we go up to 3, that would give you another point. We go up to 3 because that is the amplitude. And then at 3 pi over 2, this point, we go down to negative 3 to get your third point. And then we can connect the dots with the curve. It's going to look something like this. And it's going to approach those asymptotes, and that would be our graph. And it's worth noting that if this were a negative here, it's going to be the same idea, where it's going to go through this point, but it's going to look more like a tangent function, in the sense that over here at 3 pi over 2 is where we're going to go up 3, and then over at pi over 2 we would go down 3, and then we can create a curve with this. So it's going to look something like this. It's not the best curve, but hopefully you get the idea. It's going to look something like that. So the negative would kind of flip it around. Next, we're going to talk about graphing cosecant as well as secant functions. And for these ones both, if you can graph sine and cosine, you can then from there graph the cosecant and secant functions. So here, for example, we're graphing y equals 3 times cosecant of pi times x. Now realize that cosecant is the inverse of sine. So to begin this, we can graph the sine function. We could graph 3 times sine of pi times x. And that's what we're going to do to begin. So if you're graphing the sine function, 3 is the amplitude, and then our period we find by doing 2 pi divided by the absolute value of pi, which would just give you 2. So the period of this function would be 2, the amplitude would be 3. So the graphing of this we discussed in a previous lesson. We'll go through it kind of quickly here. And to graph the sine, okay, we can begin, let's put 0 here. And the period is 2. Let's go over here to 2. And then right here we want this location halfway between 0 and 2. We also want these two locations, which would be 1/2 and then 1.5. And we can also do some on the negative side. So over here, if we go to -2, this would be -1, this would be -1/2, and this is -1.5. So with sine, we're going to start at the point 0, 0, right here. And then the amplitude as well we need to figure out. So the amplitude is 3, so we go up 1, 2, 3, and then we go down 1, 2, -3. And here, what's going to happen is at 1/2, it's going to reach the highest point. Then at 1, it's going to come back down. That's going to be a 0. Then it's going to reach the lowest point at 1.5 down here. Then it's going to be back here at 0 when x is 2. So we can create our curve through those points. It's going to go up and down, and then back up to here. And that would be one cycle. We can do the same thing on the negative side. So to go down here, -1/2, it reaches -3. And it's going to come back up to -1, back up here, and back down here. So it's going to go down, then up, and back down to -2. So once we have this, we can then get the graph of cosecant. So to graph this, we want to first realize that cosecant, as we mentioned, is 1 over sine. Well, sine in this fraction right here cannot equal 0. So sine of x cannot equal 0. So where does sine of x equal 0? Well, sine is equal to 0 at 0, and it's going to equal 0 at pi, and then at 2 pi, 3 pi, etc. So that's the typically how that would work. Here, though, we have a little bit different because of this that affects what we have here. So basically, though, what we can do is look at the graph. Where is y equal to 0? Well, it's equal to 0 at all the zeros. So anywhere we see a 0, it's going to be undefined. So here, here, and here. Which means at those locations, we're going to have asymptotes because at those locations, okay, y cannot equal 0. This part cannot equal 0. So we're going to create asymptotes at that location. So we have this. We can do it on the negative side as well. And you can verify this graph that we're going to show you by plugging in a bunch of numbers, but it's not necessary. You can just remember what we're showing you here. And when you graph now the cosecant, the highest point is going to become the lowest point of the curve we're going to make, and it's going to look like this. So it looks kind of like a parabola, except it's bounded by these asymptotes. So that's going to be one part right there. And then here at the lowest point, we're going to have a curve going down like this. And it's going to approach the asymptotes in that direction. And we do that for each of these locations. The lowest point, again, is going to be a curve going down, approaching the asymptotes. And then at the highest point, it's going to be a curve going up, approaching the asymptotes. So again, we use the sine function. We graph that, and then from there, create asymptotes through the zeros. And then at the highest and lowest points, we created a curve that goes either up or down, approaching those asymptotes. And that is the manner in which we graph this cosecant function. And the secant function is the exact same idea. So we're not going to go through all of that because it's the same thing, where secant of x is the inverse of cosine. So you go through the same process, but instead of graphing the sine function, you graph the corresponding cosine function. And then create asymptotes at the zeros. At the highest point, create a curve going up, approaching the asymptotes. And at the lowest point, create a curve going down, approaching the asymptotes in that direction. And that concludes our lesson for today. We will see you next time.